All right, welcome to our little home studio. And in today's mini lesson in psychometrics and applied psychometrics, we're going to be studying the standard error of measurement and the closely related subject of confidence intervals. I have, of course, some slides to show you on which we can illustrate the various procedures that need to be followed. And I'll also take a minute to show you how you could do this in a spreadsheet should you be so inclined. So we're going into the slideshow mode. And here we go. Lovely blue slideshow. Okay, so the standard error of measurement, usually represented by a lowercase s with a subscript em, sometimes a subscript err, sometimes some other way. Don't worry about which. I'll tend to use sem. The standard error of measurement rests on the fact that random errors, the statistical errors that are a part of every assessment, typically follow a so-called Gaussian or normal distribution. That is, they are distributed symmetrically around a midpoint, which would be the mean score you would get if you took the test hundreds and hundreds of times, and become increasingly rare the further away you get from that. Now, you should recall from your elementary statistics class that there's a way of measuring variation within one of these distributions, and we call it the standard deviation. So the standard error of measurement is quite simply the standard deviation of the errors. So that we could say, just as we say that roughly 2/3 of cases fall within one standard deviation of the mean in any Gaussian distribution, likewise, we could say that roughly 68% of all obtained scores will fall within one standard error of the obtained score that we happen to have. That's the gist of it right there. Now, there's a pretty simple equation for deriving this. You start with the standard deviation of test scores. So you need to know what is the standard deviation of scores on my test. If this is some test you just made up, all you do is put the numbers in an array and calculate the standard deviation. In my assessment class, I would simply give you that figure, of course. But if you're doing it on your own, you can either calculate it by hand or with a spreadsheet or using a statistics program. So you need the standard deviation of test scores. The only other thing you need to know is a reliability coefficient for the test. Today's subject is not how to get a reliability coefficient. That will be covered in other presentations, but let's just assume for today that you already have some kind of reliability coefficient in front of you. Given those two figures, you quite simply take the square root of the quantity 1 minus the reliability coefficient, and then multiply that times the standard deviation. What this will mean, by the way, is that unless reliability is literally 0, unless your test is completely random, the standard error of measurement will be somewhat less than the standard deviation. Because remember, reliability coefficients always fall between 0 and 1. But they never reach 1, so you don't have to worry about the case of trying to get a square root of 0, nor realistically do they drop to 0, although they can come pretty close if you have a very bad test. That's the gist of it. Just to remind you, this is what our old friend, the normal curve, looks like. And again, roughly 2/3, 68% technically, of cases fall within one standard deviation, or in this case, one standard error. Roughly 95% fall within 2 standard deviations, or for our purposes, standard errors. And somewhat greater than 99% will fall within 3 standard deviations or standard errors. Okay, so calculating it. Again, some of you may just have looked at the formula and been like, okay, I get it, but let's walk through it step by step. So here's our first example. We have an IQ test. The reliability of the IQ test is 0.84. The standard deviation of scores on the IQ test is 15. That, by the way, is a pretty typical standard deviation for the scores we derive from IQ tests. So the standard error of measurement is equal to 15 times, the little asterisk is for multiplying, the square root of the quantity 1 minus 0.84. So the equation is now set up and we just need to follow the order of operations. So what we have is equivalent to 15 times the square root of 0.16, right? 1 minus 0.84 gives us 0.16. That in turn is equivalent to saying 15 times 0.4, because the square root of 0.16 is 0.4, just as the square root of 16 is 4. Yeah, I picked an example where it would be a whole number, so it would be kind of obvious to look at. In practice, it usually won't be. You'll want your handy dandy calculator to get the square roots. So 15 times 0.4 gives us 6. Right? 15 times 4 would be 60, but we have to the right of the decimal, so it becomes 6. There it is. And notice again, this is a pretty reasonably reliable test with 0.84 as the reliability coefficient, and that has successfully pushed the error term down from 15 all the way down to 6. Now, example 2, I'm going to go more slowly and let you set it up for yourselves. And again, those of you who are feeling confident in your basic mathematical skills will probably solve this in a jiffy, but then I'll reveal the answer to the rest of us as well. So we have a personality test with a reliability of 0.75, moderate, not terrible, not great, and a standard deviation of 10. That, again, is very typical. A lot of personality tests use t-scores where the mean is 50 and the standard deviation is 10. So we know these two facts, and from these facts, we can calculate the standard error of measurement. So setting it up, it would be 10 times the square root of the quantity 1 minus 0.75. This does give you a whole number again, because 1 minus 0.75 will be 0.25. The square root of that is 5. 5 times 5 is 25. Multiply that times 10, and you get 0.5. If you like, I can step out of the share mode for a moment, and we can try this on a whiteboard. The whiteboard does not enable me to write neatly, but let's give it a try. So what we had there was a test with reliability of 0.75. So that's the reliability coefficient. Whoops. And we had a standard deviation of 10. So setting the equation up, we could say that the standard error of measurement was equal to 10 times the square root of the quantity 1 minus 0.75. Now again, following our little order of operations as usual, we first do the stuff underneath the square root sign here. That gives us 0.25. And now again, if this wasn't such an easy one, you would definitely want to call up your calculator to derive the square root. But when it's one that gives you a whole number, we're all set. So we can just say 0.5, which again, basically now we're saying half of, oops, I don't want that decimal. We'll just write over it. We're saying half of 10, which is to say 5. And that's it. Okay, back into the slideshow we go. Okay, so the next subject is confidence intervals. And confidence intervals are derived, in fact, from the standard error of measurement. So here's the thing. When you do an assessment of any kind, you administer a test of any kind, you know that the score that you're obtaining is really only an estimate of the true score, because there is that pesky random error that's always built in. But if we know the standard error of measurement of the test, we can figure out a range of scores within which the true score is likely to fall. And I emphasize the word likely because it's never going to be 100% sure, but you can set whatever level of confidence you wish and run the numbers accordingly. So if you only want to be 75% sure, go ahead. If you want to be 90% sure, go ahead. And I'll show you how to do this as we move forward. So again, you specify the level of confidence you want. There are some conventions here. One possibility, which is a pretty conservative one, a pretty stringent one, is to say, I want to be 95% sure that the score that this person really should have gotten on the test falls within this range. So these would be 95% confidence intervals, usually abbreviated CI. And so you might, in a test report, for example, see somebody writing that 95% confidence intervals for a child's score on an achievement test fall between 104 and 112. In fact, that's the confidence interval, that range of scores. And all that really means is that the child's true score on whatever achievement domain we're assessing is probably between 104 and 112. If this was on the IQ type scale, that means they're probably in the average to high average range. Now, understandably, a student could ask, and that would be in some ways an intelligent question, really, why do I want to know this? Fair question. A hint at the answer? We don't test for no reason. Now, sometimes we're simply conducting research, and we're conducting research on large samples of people, and where an individual score might fall really doesn't matter all that much, as long as we know that, broadly speaking, we're in the ballpark. But that's not true if you're conducting an assessment of one person as part of a decision-making process. Will this person be eligible for services is a really important example here. And it might be that unless your score crosses a certain threshold, you're not going to be eligible for services. So what about the case where the score you get is really close? It's on one side or the other of that threshold. Well, the fact is, because there's error built into your test, and there's no way not to have this, because of that built-in error, you could be looking at someone who actually falls on either side of that threshold. And in such cases, these are ambiguous cases, right? In such cases, you'd want to take into account all the other information you have available before making a final recommendation. That's why it matters. Okay. So calculating confidence intervals. It's actually remarkably simple. If you have the standard error of measurement, all you need beyond that is what the person got as a score. Because remember, the score you got is your single best estimate of where the true score is. But there is error around that. So we would typically say that the obtained score is going to be right smack in the middle of the so-called confidence interval. There is an exception to that, which is more advanced than we need to worry about. Some of the commercially published IQ and achievement tests use a slightly different procedure, but fundamentally, it's still the same idea. So the confidence interval is a range of scores from the lowest possible value to the highest possible value that the true score is likely to have. Again, at whatever level of confidence you want it to be. So if, you can say 90%, you can say 70%. That's up to you, as long as you can make a case for why you picked that level of confidence. So what determines the confidence interval? Partly it is exactly that. It's how much confidence you want to have that your range, your interval, captures the true score. And the other factor is the reliability of the measurement. Because, as you may recall from a few minutes back, the more reliable the test, the smaller the standard error. Now, there is, then what you have to do is to say, well, how many standard errors out do I have to go from the score I got? And to determine that, you typically just look at a little table. I'll show you a sample on the next slide. It's a table you'll find in the back of any statistics textbook, and you can easily find these online as well. It's the table that shows the area under the normal curve. Okay, so here we go. That's what the table looks like. So you'll remember z-scores from elementary statistics. Z-score of 0, of course, means you're right at the mean. In this case, that would mean you're exactly at the score that you obtained. And as you count out in z-scores, you're getting further and further away from the mean on that old normal curve. The area we're concerned with here is the column headed z to mean. So you have the table in front of you. You have decided how confident you want to be here. So let's say you say, I want to be 80% sure, 4-to-1 odds that the true score falls within the range I'm specifying. Okay, that was your decision. Now, in this column z to mean, I'm going to want to find the value that's closest to 1/2 of that. Half because we're going in 2 directions, and this is only giving us z to the mean, so we have to have it on both sides of the mean there. So if I'm at 0.80, cutting that in half, I'm at 0.40. So all I need to do is scroll down here until I find the value that is closest to 0.40, which happens to be here. Yeah, if you want to be real persnickety, you could get a table that would go even further, more precise than that, but this is good enough for most everyday purposes. So I found 0.40, or as close as I could get to it. Now I just go over to the z-score column and I look for the z, and that's actually going to be my multiplier. So, if I had set this to a different number, let's say I had set it to, for some reason, 89%. So now I'm looking for 44.5. I'm not sure why I would ever do that, but I would scroll down, until I found, look at that. 0.445 is about half of 0.89, and I would have picked 1.6 as my multiplier. 80%, by the way, is not an unreasonable choice. So what I can say is, with 80% confidence, the person's true score on the test falls within 1.3 standard errors of the score that we actually got. That will be their confidence intervals. Now, if you happen to be a student in one of my assessment classes, any work I assigned, I keep this as simple as possible. So I'll either say 68% confidence intervals, which means the z is 1, so you multiply by 1, or I'll say 95% confidence intervals, which basically gives you a z of 2, and you just use the z of 2. I think it's technically 1.96, but 2 is close enough. So just to keep life a little easier. So calculating them, here we have an IQ test. The standard error of measurement is 4. We've already determined that on the basis of the reliability of the test, which we determined in some other way. And so Juanita takes the IQ test, and she gets an IQ of a score of 108. Now, again, 108 is our best guess of her true IQ. But because there is random error built in here, it could easily be a few points off one way or another. So if I wanted 68% confidence intervals, well, the low end would be 108 minus 1. Remember, the 68, the z was going to be 1 times the standard error, 4. And the high end would be 108 plus 1 times 4. So obviously 1 times 4 is 4. 108 minus 4 gives me 104. 108 plus 4 gives me 112. So I'm 68% sure that her true score falls between 104 and 112. Her 95% confidence intervals, if I preferred to report those, would be 2 standard errors out. So you'd go 108 minus 2 times 4 up to 108 plus 2 times 4. 2 times 4 being 8. 108 minus 8 brings us down to 100. 108 plus 8 brings us up to 116. And so now let's have you try one. Again, I'll walk you through it as well, but our little friend Alfonso obtains an IQ score of just 74. Poor little Alfonso. So what are the confidence intervals around Alfonso's scores? 68%, 95%. Again, 68% is going to be just one standard error out in either direction. So that means 4 points. So what you're saying is we're 68% sure that his true score falls within 4 points of whatever we got. So it's 74 minus 4, 70, 2, 74 plus 4, 78. 95% confidence intervals. Now you have to go out 2 standard errors. That's 8 points away. So notice there's kind of an inverse relationship here, right? If the more confident you want to be, the more error is possible, the less sure you are, or the less narrow the range of scores that you're willing to specify is. Now, I did say I would show you how to do this on a spreadsheet. So we're going to go into a new share here and see how we do. Okay, so here, again, we're just going to say that we know the reliability. So for whatever test we're using, I'm just making up a number, the reliability turns out to be 0.83. Now, if I want to get the standard error here, what I can do in a spreadsheet environment is simply to type the equation in such a way that it captures this value. So the standard error here is going to be, I needed to specify a standard deviation as well. So let's make the standard deviation 10. Sorry about that. Needed to have that at some point. And so the standard error, again, is equal to B2, which is the standard error, times the square root of 1 minus A2. Boom, boom, boom. Okay, so the standard error is 4.123106. Of course, you can always round that off. Now, let's say that somebody obtains a score on the test of 45. This might be one of those T-score tests where the mean is 50. Okay, well, the 68% confidence interval, again, is from a low score to a high score. What I would do to get the low end is simply to take the obtained score. Notice it highlights it there, so you know that you're pointing at the right little cell. And we're going to say, take that minus C2. And there we are. The high end is going to be E2 plus C2. And there we are. 95% is going to be pretty much the same idea. E2 minus, only now it's 2 times C2, right? Up to E2 plus 2 times C2. Notice what I'm doing in each case is simply, whoops, what did I do? I didn't put equal. There we go. I'm simply going in and naming the cells I'm concerned with. And formatting, by the way, you don't want to go 5 places to the right of the decimal. So let's just format the cells to number format. 2 places to the right of the decimal should be fine, and there we go. So the range is from 40.88. Honestly, you could even round that up to 41 because you get fractional test scores up to 49.12. So basically 41 to 49 is the range within which we are reasonably confident, better than 2 to 1 odds, that this person's true score falls. 36, 37 up to about 53 is the range within which we're like 95% sure their score falls. Again, spreadsheets can be quite handy for this if you need to do a number of cases for some reason. Otherwise, you're probably just as well off doing it by hand with your handheld calculator and so forth. That said, we are going to go for a moment back into the slides, and we're going to wrap up in just a minute. Oh yeah, that second case, by the way, Alfonso, that shows us why confidence intervals are so important. An IQ score of 70 can be a very important threshold in some assessments, where if you're below 70, you might be considered intellectually disabled, which would free up considerable services for you. Whereas if you're above that threshold, it's going to be much harder to make a case for an intellectual disability diagnosis. The fact that his 95% confidence intervals straddle the line would help you to make that case. If you believed, based on other evidence, that Alfonso really needed special education services, you could advocate here. So, wrapping up, remember, all measurements involve error. Therefore, understanding how much error is baked in to the test we're using is important. That's what the standard error of measurement is for. If you're reporting on any psychological or educational or other test, frankly, it's a figure that should be reported. Confidence intervals can be constructed around any obtained score based on the already known standard error of measurement. High-grade commercially published tests will actually often have a page or two of just a table of numbers of confidence intervals. So they'll give you the 85% and 95% confidence intervals around every possible score. But if that's not there, you can get them for yourself, as we just did today. Remember always, the score you get on an individual case is only a point estimate. Random error is always present to varying degrees. So the confidence interval is giving you the range of scores within which the true score is likely to fall. And at that point, we are done for the moment, and I'm going to say good day.